Hi, my name is Caroline Porterfield, and this is my Physics 2212 lab report for on bar magnets. Today, we will go over an introduction, some models, the experiment itself, the code, discussion of the data, and some conclusions. The purpose of this lab is to measure the distance-dependent magnetic field of a small bar magnet. A quick overview of the results is n is equal to negative 2.676, and the magnetic dipole moment was calculated to be 3.8837. The system was the bar magnet, and the surroundings was everything else. The analysis was done using GlowScript, and we created a computational model to determine the theoretical magnetic field. We then compared observed versus predicted distances of on and off axis magnetic fields. The fundamental physics principles for this lab are the Biot-Savart law, magnetic field of a dipole, and the distance dependence formula. The Biot-Savart law relates the magnetic field at any point to a tiny current element. The formula used for this is shown. B is the magnetic field at the observation point, mu is the magnetic constant, and Q is the charge of the particle. V is the velocity vector of the particle, r hat is the unit vector from the charge to the point, and r is the vector from the particle to the observation point. The magnetic field of a dipole is a closed circulation of an electric current system. The formula is shown and observes, and it shows the observation point is not at the location of the dipole. The distance dependency formula is the magnitude of the magnetic field due to a bar magnet as it falls off with distance. Two equations are shown. B bar is the magnitude of the magnetic field, r is the distance from the source, and k is the proportionality constant, and n is the distance exponent. The other equation is the linearized form. The experimental setup began with orienting the phone to make the magnetometer orthogonal to Earth's magnetic field. Then we found the location of the magnetometer chip on the phone and then measured the distance between the magnetometer and the bar magnet for on and off axis. This can be seen in the pictures shown. Now the data analysis of on axis. On the left is the distance measurements for different magnetic field strengths. And on the right is the graph of the linearization plot of the averages. This is based on the distance dependency formula and the equation of the best fit line. This was then used to determine the values of n and k. Now, calculations. Since we know n and k, we can solve for the magnetic dipole moment, mu. This was found to be 3.8837 amp meters squared. Now, the data analysis of the off axis. Very same to what we did for on axis. The magnetometer is now perpendicular to the direction of the axis. You can see that the x, y, and z components for the magnetic fields that are perpendicular distance of about 1.76 meters. Now the computational model initial conditions. The function for magnetic fields were created and we plugged in our magnitude of the magnetic moment, as you can see here. Next, the code for the visual aspect took place. I created lots of arrows for on and off axis. I had to specify the magnitude and direction for all of them. 2 are on and 4 are off. One arrow is 45 degrees from the axis, as you can see, and the predicted magnetic field is shown in the code, which is similar to ours. The similarities and differences for our observed and computational models are shown. As you can see, the values are very similar, but there are still some differences. Let's look at some possible errors as to why this occurred. Our first assumption was that the bar magnet acts as a magnetic dipole. Our next assumption was that the magnetic field falls off as distance increases. Our first possible source of error was that other objects nearby that were electronic or magnetic may have skewed the data on our magnetometer. Another source of error was that the exact location of the magnetometer was not found precisely. Some observed statements were, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x-component of the magnetic field increases. Now for the discussion. What if you hadn't oriented our experiment to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The Earth's magnetic field would interfere with the bar magnet's magnetic field, which would mess up the results. And what if you were to stick two identical magnets together end to end and had run this exact same experiment? How would you expect your measurements to differ? The magnetic field's magnitude would then double, but the direction of it would stay the same. In conclusion, we learned all about bar magnets, and how to calculate the magnetic dipole moment. Thank you for watching.